right? So we have the first quarter being called with this function. We have the second quarter being called maybe with this function, that is from n by 4 plus 1. I'm going to type it as n by 4 to n by 2, and maybe I'm going to call the third array as from 3n by 4 n. Now here I'm not calling all of the segments of calling this function for all of my segments of this array, because I'm not calling this function for let's see, n by 2 to n by 3n by 4. Right, I'm not calling this particular function, but again, basically I'm calling my function thrice. Each time I'm calling it with quarter size of my array, right? So that would be an example of 3tn by 4 complexity. Okay, so now what would these complexities look like in terms of recursion trees? So the first one, let's look at the unbalanced tree. The unbalanced merge sort would be tn by 3 plus t2n by 3 plus of n. Now we know that the merging complexity for the first level is going to be Cn. So that is the time complexity for the first one. And we divide this array into two parts, not equal parts, but again, two different parts. The first part is Cn by 3. And the second part is C of 2n by 3. That is the merge complexity of that part. Then we continue doing this until we reach all the leaves. So we have Cn by 9, C2n by 9, and C2n by 9, and C4n by 9. Each time it's an unbalanced merge sort. So each time we are dividing it into two unbalanced arrays. So the time complexity of this particular recurrence model would be, each time we have a merging complexity of Cn, where we have Cn as the first level's merging complexity. Cn by 3 and C2n by 3 would be also Cn. Summation of both of those would become Cn. And again, summation of all of these things, merging them together, would again give us Cn, right? Because each time we are still bothered with the entire array every time, and then we are merging them together to get the same complexity as Cn. So here, every time we have a time complexity of Cn. And how many Cn's do we have? We essentially have the same number of Cn's as we did for our other merge sort example. We have as the number of levels that we have in our tree, right? So the height of our tree. Now, if it was a binary tree, the height of our tree would have been log base 2 of the number of nodes, or n, right? So number of leaves, or n. Now, since this is an unbalanced binary tree, we are not guaranteed that we are again going to have log base 2, right? It's not going to be log base 2 because we are not dividing it into two halves, but we are actually dividing it into 1/3 and 2/3, right? So in this case, the height of our tree is going to be log base of 3 by 2 n, right? So if we have log base of 3 by 2 n, and we have Cn for each level, then we have the complexity of Cn times log base 3 by 2 of n. Again, either case, it is the time complexity again becomes big O of n log n, right? So even if it's an unbalanced merge sort, we are still going to get our complexity of n log n. Now comes another example, that is, every time we are dividing our tree, we are dividing it into dividing our problem into quarters, and we are only bothered with 3 of those parts. And combining those quarters require n squared time complexity. So initially we have Cn squared as our first time complexity. Then we have Tn by 4, Tn by 4, and Tn by 4. So 3 Tn by 4s are being divided for our first recursion call. Now each of those combinations requires Cn squared, Cn by 4 squared, right? Every time, because it is n squared merging complexity. And we are again dividing it into 3 subhalves, that is n by 16, n by 16, and n by 16. So, right? So here we have our time complexity as the first level is Cn squared. Then we have 3 times n by 4 squared. So 3 times Cn squared by 16. Then we have 3 by 16 squared Cn squared all the way to n log base 4 of 3. Right? So does everyone understand that every time we have Cn squared, 3 by 16 Cn squared, 3 by 16 squared Cn squared, 3 by 16 cubed Cn squared, for a level of log base 4 of n. Now, if this is the case, can someone tell me, Brian, are you talking about this particular thing, log base 3 by 2n? Yes, so since we are not divide, so remember why the log, where the log base 2 of our binary tree comes from. The log base 2 comes because we are dividing it into 2 parts, right? Here we are not dividing it into 2 equal halves. We are only dividing it into 1/3 and 2/3 parts, right? So if we have 1/3 and 2/3 parts, then the log base 2 becomes, for the first part, we have n by 3. So if it was equally divided into 3 components, we have log base 3. But here we don't have equal components for log base 3. We have log base 3 as the first part and 2 by 3 for the second part, right? So that is why we get log base 3 by 2 of n. Now, it's not, okay, how should I explain? It's not exactly the invert of the higher fraction. It is essentially, think about it like this. We are now dividing our array into 1.5 parts every time, not 2 parts, but 1.5 parts, because we have the first third and the other part. So 2n by 3 is 1, and we have half of that. So we have 1.5 times dividing our array. So that is where the 3 by 2 comes from. Does that make sense? Because 2n by 3 means 2/3 of the part. So consider that as 1 part, right? The other part is half of that. N by 3 is going to be half of 2n by 3. So essentially we have 1 part and we have the other part that is half of this part. So the total number of things that we are dividing it into is going to be 3n by 2, right? Because it is 1.5 times. If you think about it in terms of the binary tree, we have 1 and 1. So each of them are, yeah, exactly. Each of them are the same thing. So combining all of them together, we have 2. Yes. That is just the intuitive way of thinking about this. Okay, so coming back to this thing, we have Cn squared, 3 by 16 Cn squared, and so on. Now, can someone tell me if the size of my height of my tree? Okay, so we have Cn squared, 3 by 16 Cn squared, and so on. Now, can someone tell me why we have a complexity of n squared here when the height of our tree is log base 4 of n? Why do we have a time complexity of n squared here? What is the total time complexity of this tree? It is Cn squared plus 3 by 16 Cn squared plus 3 by 16 squared Cn squared. So should it be, why do we have Cn squared? Because the time complexity for merging these 3 parts is going to be n squared. So some constant times n squared. So that is why we have Cn squared. Is that what you're asking, Aman?
No, I don't understand. If you have like n elements in an array, why are we dividing Cn squared times the array into 3 parts? I didn't get the top part of this diagram.
Okay, let me just explain this again. So we have, yeah, don't worry. So we have this merging part. This merging part is the time complexity for merging all of these divided components together, right? So in this particular case, for the unbalanced merge sort, our time complexity was n. So we have some constant times n as our merging complexity. Now, when we divided these into 2 parts, the summation of these 2 components was Cn by 3 plus C2n by 3. That ended up being Cn, right? Because more or less it is still some constant times n by 3 and some constant times 2n by 3, summation becomes Cn. Now that n comes from this particular merging complexity. In this case, we have the merging complexity of n squared. So let's think about an algorithm where we divided our array and then we are sort of bubble sorting the array back for some weird reason, right? So in that particular case, the merging complexity is Cn squared, right? So then we are dividing this array into 4 parts, but we are calling the function recursively 3 times, right? So if we are calling this function 3 times, the time complexity for these become Tn by 4 and Tn by 4 and so on. Now merging those in accordance with where n becomes n by 4, now becomes Cn squared by 4, Cn squared by 4, Cn by 4 squared, Cn by 4 squared, and Cn by 4 squared, right? Now we have Cn squared by 16 and so on, but n is n by 4. The next time when we divide this array again, we have Tn by 16, Tn by 16 and so on, right? Again, we are dividing it into 4 parts and calling it thrice. So the time complexity for this particular merging level is Cn by 4 squared, right? So that is Cn squared by 16. So we have Cn squared by 16, 3 of them. So we have 3 by 16 Cn squared. For the next part, we have Cn by 16 squared. So that is for each of them. For each of them, we have 3 by 16 squared, right? And we have C, and then we have n squared, right? So that is the time complexity for merging this entire thing, where we have the time complexity of 3 by 16, because each time we are dividing it into 3 parts. So the math turns out to be 3 by 16 squared and C n squared. For the next level, we again divide it into 3 parts, where each part is n by 4. So 16 times 4, 16 times 4 basically becomes 64. So we have n by 16 cubed. So 3 by 16 cubed. And then essentially we have 3 by 6. The next one becomes 3 by 16 cubed Cn squared. The next one becomes 3 by 16 to the power of 4 Cn squared. Does that make sense? Do you want me to write it up? I will write it up. Okay. The first time we have C of n squared. Then we have 3 times C of n by 4 squared. That gets us 3 by 16 n squared. Yes, but it is not going to be 3 by 16 to the power of n. It is going to be 3 by 16 to the power of log of n. That is the number of, that is the height of our tree. No, it is log of n. Yes, Sean, you are right. It is n squared is the merge part, exactly. Now, next time that we are again dividing this tree, we have for each of those Cn squared by 4, we have a merge complexity of Cn by 16 squared, Cn by 16 squared, Cn by 16 squared, right? Now, so that becomes Cn squared by 16, Cn squared by 16, Cn squared by 16 squared, Cn squared by 16 squared. And we have a total of 9 of this. So that is basically